So if we're going to be using superposition, we need our signals to be small. So how small exactly do we need our signals to be? Well, in order to define that more clearly, let's consider this simple circuit below. So you can see this looks very similar to what we considered when we were looking at BJTs, and we're going to notice that's going to be true throughout this unit. So we have an in-channel enhancement mode MOSFET sort of at the heart of our circuit here. We have our single drain resistance RD with some voltage source VDD. And then at the gate, which is acting as our input here, we have some small signal input V sub I, as well as some DC input VGSQ. And our output is defined over here off of our drain side. And so what we need to keep in mind, and this will be made more clear in some examples later on, is that our Q point is going to be set by a lot of these DC values. So our VGSQ, our VDD, as well as our RD is going to be setting our Q point value. And then remember that Q point value is going to act sort of as, we could think of it like a base camp, where our AC values are going to be deviating from. So let's just go ahead and remind ourselves our Q point is going to be set by our VGSQ, so the DC value, the VDD, and that drain resistance R sub D. Okay, so you'll notice if you look at any of these parameters for our currents and voltages, we have that lowercase parameter uppercase subscript. And so what that means is that any of these parameters is the sum of their AC and DC components. So let's sort of focus in on this VGS first. So what that means is we could say this VGS is equal to the DC component, which is VGSQ, plus some AC component, lowercase VGS. And in this particular case, based on looking at this loop here for our gate to source, we can say that we have that lowercase VGS is actually just going to be VI. So we could also say this is equal to VGSQ plus lowercase VI. And so let's call this, to be consistent with our notes, equation 1. We could do well, not a similar thing, we're not going to get there quite yet, but remember that we said for linear amplification we want to be operating in the saturation mode, or in the saturation region. So if our MOSFET is in saturation, what that means is that we're going to have a drain current given by I sub D is equal to Kn times VGS minus VTN, and then that quantity squared. And so this is just our general equation. Of course, VTN is our threshold voltage, K sub n is our conduction parameter. And notice for our drain current and our gate to source voltage, I've used those sort of lowercase parameter, uppercase subscript to indicate that we have a DC and AC component. So let's call this equation 2. And so now what we're going to do is we're basically just going to substitute equation 1 into equation 2. So we're going to take this combination of VGS and we're going to plug that into our VGS down here. And we're going to get sort of an expanded version of our drain current. So we can then say that our ID is going to be equal to Kn times VGSQ plus our lowercase v, lowercase gs, so the AC component, minus the threshold voltage, VTN, all of that squared. And so we could play around with this and we could get the DC components together, because remember our threshold voltage ideally is just going to be one fixed value. So we can say this is equal to Kn times the quantity of VGSQ minus VTN, so that is sort of our DC value, plus our AC value, which is our lowercase v, lowercase gs. And so that, of course, is still squared. So now we can just sort of factor that out, multiply that out, and what we get is that our drain current is going to be equal to Kn times, we're going to have that first term. So if it's easier to visualize, you can think of this whole parameter as being some parameter. You could call it x, whatever you want. So we're going to have x squared. So our x is VGSQ minus VTN, so that parameter squared, plus 2 times x times lowercase VGS. So 2, and we have that Kn out front as well. So VGSQ minus VTN times the lowercase VGS. And then finally, we get this second term in the brackets there squared. So we have the Kn out front still times our lowercase VGS squared. And so looking at this equation, we can now define what we mean by a small signal. And so we're going to focus in on this third of our three terms here. And so it turns out we want to keep that really small because this term is going to be producing undesirable harmonic effects. So it produces undesirable harmonics. Okay, so we want that to be small, obviously. We don't want to have these undesirable effects. And so we don't necessarily have a specific number like we looked at with our BJTs, but what we can say is we want that term to be negligible compared to this second term. So we can then say our small signal condition for linear amplifiers is given by, so small signal condition for our linear amps is going to be given by that VGS is going to be much less than this second term, so 2 times VGS, sorry, that should be a capital, so VGSQ minus VTM. And so of course we've just sort of divided a VGS on both sides. So if we come back up here and we're looking at our second and third terms, we can just divide out a lowercase VGS in each of those. So we want that third term to be much less than the second term is essentially what we're saying. So this is the condition that we need to be met, we need to have met in order to consider this to be a small signal circuit. Okay, so what we can do then is we can say for most practical cases, we're going to design for that so we can neglect that third term. So let's say we're just going to neglect that so we can look at just these first two terms. So let's copy this and bring this down here. And then what we're going to do is we're going to say, well, just like we considered our VGS from the start, we know that really our IDQ is just our ID. So let me write this so I don't get myself mixed up here. So our ID is really just equal to IDQ plus some AC drain current, I sub Z. And so what we can see from that then is that just comparing these, this first term is our DC part, and this second term here is our AC component. So this is DC and AC component of our drain current. So with that, what we can do, focusing on that AC part, so our AC part of our drain current is I sub D is equal to 2Kn times VGSQ minus VTN times our VGS. And so from this, we can define a very important parameter for our transistor called the transistor transconductance. So our transistor transconductance is defined as GM, and so in general our GM is going to be ID over lowercase v lowercase gs, and so of course from this equation we just divide both sides through by that lowercase vgs, and so that's going to cancel it out on the right, and we see that that's just equal to 2Kn times VGSQ minus VTN. Okay, and so we can actually simplify this expression a little bit more. If we look at the form for our DC drain current up here, so we can utilize this and we can get this a little bit more simplified. And so remember, that's our IDQ. We can rewrite this and we can say that our GM is equal to 2 times the square root of Kn times IDQ. And so that's a little bit easier to see if we just come up to this expression and we multiply by Kn, we're basically squaring that. So then square root of that is going to be Kn times our VGSQ minus VTN, and then we have the 2 out front. So let me get rid of that 2 up there so we don't mistake that for part of our original equation. And so again, this is our transconductance of the transistor, and we can think of this as the gain of our transistor. And as we're going to see in a later video, this is going to be an important parameter as we're making a small signal model of the transistor. And just like we saw with our BJTs, this small signal model for our AC analysis is dependent on our DC analysis. So we're going to want to do the DC analysis first. We figure out where our Q point is, and from there we can figure out what is going on in terms of our AC analysis. So another thing to note too, looking at this, is we can see that our GM is proportional to our conduction parameter Kn, and we can see that well, we can't see it here, but from previous notes, we know that our conduction parameter is proportional to our width to length ratio of the transistor. So this is an important design parameter, as we've seen before. is that if we're actually designing the transistor layout in an integrated circuit or for a discrete device, we can design for a given gain based on that width to length ratio. So a couple other things that we want to look at real quick is let's consider this same idea of what is small signal graphically. So we did a similar thing as we were looking at our BJTs. So if we consider this small signal graphically, and I had that earlier and then I copied something else, so let me just quickly redo this. So we're going to plot our drain current versus our VGS. And so remember, if we don't have a threshold voltage, we essentially don't have any current. Now in practice, we're going to have a little bit of current called the subthreshold current, but let's assume it's 0 until we get to VTN, and then we have some increasing current as we increase our gate to source voltage. We're going to have some point in here that is our Q point, and so we're going to have some corresponding IDQ and VGSQ. And so what we're saying is if we send in some AC signal on our VGS, so let's say we send in some time varying signal on our VGS, then of course we're going to get some time varying signal on our output. And ultimately what we're doing when we're using this small signal analysis, similar to our BJTs, is we're using a linear approximation right here around our Q point. So we're doing something like this. And so the idea is we don't want to be deviating too far, because if we're deviating too far, then of course this linear approximation, for instance up here, is no longer a very good approximation. But if we keep that VGSQ signal small enough, we're not deviating very far. And you can see that purple line, which is our linear approximation, is going to be a pretty good representation of what our amplifier is going to do. So of course we could draw a line up here corresponding to the peaks, and of course we see we're going to have some variation in our VGS, so that's going to be going a little bit above and below our VGSQ, and we're going to have a corresponding variation in our IDSQ. So for instance, we would have something that looks like this then as our output IDSQ current. So one other thing to look at though is, remember, our IDQ wasn't defined as our output. So if we go all the way back to that circuit we were considering, our output was actually defined as this voltage here, which we can see in this particular circuit is just equal to our VDS voltage. So let's come back and talk about our VDS voltage a little bit more. And so we're going to look at it in terms of doing a KVL loop on this drain to source loop. So let's come down here. And we can say, you know, we had already talked about our small signal parameters for our gate to source input. So we said that was VI. We already defined our small signal drain current. And so using our transconductance, we can just say that that is GM times the small signal gate to source voltage. And now we want to say, well, what about our small signal output voltage, which is equal to the small signal drain to source voltage? And so the same basic idea is we can say our overall drain to source voltage is equal to the overall output voltage, and that is equal to the VDD minus our ID, and so this should be our overall ID, times our RD. So that's just from KVL on that drain to source loop. And so then of course we plug in for our IDQ and our ID, so we have this becomes VDD minus, and then our ID is our DC component plus our AC component times RD. And we can then separate, so if we multiply this term out, we're going to get an AC component and a DC component. So we can say that our overall V out is equal to some DC component, which is VDD minus IDQ times RD minus lowercase id times RD. So this first term here is our DC component, and the second term here is our AC component.